All right, so let's see, let's get going for today. So what I want to do is today finish up our discussion on the microscopic picture of superconductivity, and then kind of introduce also the next topic, which is also related to superconductivity, but occurs not so much in the many particle, not in such a macroscopic many particle picture, but even in a single particle picture, and it has some very interesting analogies to superconductors, except it occurs in semiconductors, which is the integer quantum Hall effect. So we will kind of make this transition from superconductivity to integer quantum Hall effect, and that will be our kind of way of understanding the aspects of topological properties that have emerged in quantum transport in materials over the past couple of decades. So, okay, so we have been discussing about superconductivity. In the last class, we saw a few cases of junctions, metal superconductor junctions, Josephson junctions, and talked a little bit about their transport properties. But we still haven't really explained microscopically what is the origin of superconductivity. What we did discuss in a qualitative manner in the last class was ideas of Landau and Ginzburg, which is got to do with phase transitions and thermodynamics. They considered the transition from a normal metal state to a superconducting state as similar to a phase transition from, say, water to ice, condensation and emergence of some, or breaking of some symmetries. In water, the motions of the water molecules can go in every which way, but in ice it's ordered and it's a crystal, so you have broken certain rotational and certain other symmetries. And in a very from that analogy, Ginzburg and Landau tried to propose, or not tried to, they did propose an argument based on the free energy of the superconductor, which includes the free energy of the normal metal and terms that are brought about because of this condensation. If you form this macroscopic wave function, it would have a few terms. There would be a kinetic energy term of this whole rigid macroscopic wave function. This we have discussed earlier. This is the p squared by 2m sort of term. And then you have, this is the potential term, and they expanded it in terms of psi squared and psi 4. This is sort of a Taylor series by saying that this is what captures the Meissner expulsion of the magnetic field. Whenever you expel magnetic field from a region, you gain a certain amount of energy. So the system can, in that volume, the system can lower its energy by proportional to the square of the magnetic field, because energy stored in a magnetic field goes as b squared by b squared by twice the mu naught of that region. So they said that this must be related to the critical Meissner field, and then if there are some other magnetic fields left inside the material, you have to pay the price, so there's an increase in energy. Anyway, so from here they were able to explain that if your alpha, which is the coefficient here, is positive, then the total free energy has only one minima. But if alpha becomes negative, then this functional here, as a function of psi, will have 2, and the minima here is, this is, and the system goes into this state rather than that state, and that's the superconducting state. And from here, they're able to relate the alpha to the Tc. Clearly, above Tc, if alpha is proportional to T minus Tc, above Tc, the alpha is positive, and below Tc it's negative. So it undergoes that phase transition, and from here they immediately are able to obtain what we also obtained earlier from classical intuition, the Meissner, the London penetration depth of how far inside a superconductor does the magnetic field penetrate. that depends on the number of superconducting carriers or Cooper pairs, as we will talk about them today. And they also are able to explain something called a coherence length, and that's going to be our point where we will start discussing the microscopic picture of quantum transport, or the reason for superconductivity in the first place. And the yeah.
So is this like beta over 2 side of the fourth term? Is that just empirical, or
this term here? Yeah. So this is what you call as a phenomenological introduction. It was introduced to. So whenever you have an x square and an x4 term, right, and the x square coefficient goes negative, you will get this sort of feature. So they tried to kind of understand why is there a phase transition, and they said I must have something like this. Okay. And therefore the argument they turned it around and said that I want to write the free energy reduction due to, say, expulsion of magnetic field, okay, because that what expels the magnetic field is this condensate itself when it forms, right, and it circulates currents around the loop. And so they said that it must depend on psi, and whatever function it is. We also know that the current depends on psi square, if you remember. It's the carrier density. It's the microscopic carrier density. And so they were trying to write the energy as a function of the current, and whether current goes this way or that way, it doesn't, the energy doesn't change. So it's only the even powers, j squared, j4, and so on. So that's why there were many reasons to write it this way, okay, and the even terms are missing here. Okay, so you can read. It's a pretty rich body of literature in itself, and but this did not give you any direct hints of what is the microscopic origin, and that was developed, about 6-7 years later by Boydin, Cooper, and Schleifer. And the reason they did not have that many hints about the microscopic picture because there were no experimental data to, give any hints at that time as to what is going on inside the material with electrons and phonons and other things. And then later on, after Boydin-Cooper-Schleifer theory was developed, it was shown by Gorkov and others that these are exactly the same thing. BCS theory, when you look at it as a bigger picture, it follows the Landau-Ginzburg theory, except it has a lot more microscopic details now. And so, yeah. Okay, so here's a parameter. It's called the coherence length, and we are going to actually look at that now. And it's effectively the size of a Cooper pair, but first we need to discuss what is the reason for the formation of a Cooper pair in the first place, right? So that's the first thing we want to discuss, and that hint came from the Frohlich's ideas. Which is related to the electron-phonon interaction, something that you have been calculating, for example, phonon scattering, say deformation potential phonon scattering, and that it's related to that microscopic mechanism. And so the experimental data was available right after a few years after the Landau-Ginzburg theory was what's called the isotope effect in actually right around that time. It says 1950s, not even 53. So what they were measuring is superconductivity. For example, here it's in mercury, and what they find is this critical transition temperature, which clearly holds a lot of secrets of what is microscopically going on inside the material. The transition temperature was, the lighter was the mass, the larger is the transition temperature, and it goes as mass of the atoms. It basically increased with the decreasing mass. Lighter is the mass, higher is the TC. So that was as a square root. So this is what's shown here, and we also know from this mass spring picture of phonons that the frequency or the energy of the phonons, is basically square root of a certain constant, spring constant by the mass, right? So we know that. So and that gave a hint that the phonons are probably playing a big role or playing a role in causing this condensation microscopically, and what the reason for electrons to, instead of repelling, to attract, and then form one condensate object, one object which is a condensate which holds for all the Cooper pairs in the material. Okay, so let's look at it microscopically now and see how one might try to understand this idea. So before we go into the microscopics, I just want to kind of also add a few things. Qualitatively, you can imagine that if I have two electrons, they are both fermions, right? And they would not like to be in the same state at all. They would avoid as much as possible to be in the same state. On the other hand, if I have two bosons, so let's say electron 1 and electron 2, but if I have two bosons, there's no problem. In fact, they would rather be in the same state. That's the lowest energy system. All right. If I have two bosons, they would. There's no Pauli exclusion principle for them, and so they can. We can see why they might condense. That's a lowering of the energy of the system. Whereas for fermions, because of the exclusion principle, when I have a metal, for example, and I start looking at what are the states that the electrons in say a three-dimensional metal can take, we know that in a crystal the electron states we can index them by their k values, right? K being kx, ky, kz, and we know it's all discrete depending upon the size of the metal and so on. But essentially, there's a grid of 2 pi by lx, 2 pi by ly, 2 pi by lz in the k space. And then when you put in a large number of electrons, what do? They will basically fill up all the way to a sphere or some non-spherical Fermi surface. Those are not very important at this point of time, but they'll fill up k space from the origin, from the lowest energy, all the way upwards to a certain radius, which is the Fermi kf, right? So they'll fill this thing up till kf, and then the energy, the maxima will be EF, right? And that is h square kf square by twice the mass of the electron, and this is the free electron, right? That much we know. This is the Fermi surface. So it's basically a rigid sphere inside which all the states are filled, and outside which it's all empty, right? And how is kf and all related to the particle number? That I think you hopefully are very comfortable with that. So the volume of the sphere is 4 by 3rd pi kf cubed in the k space, and you know that the total number of states inside are 2 pi by L. Each little cube here to which one quantum state is attached has a volume of this much. That much. These are things we already know, and then 2 times that, because each state can hold an up and down spin, and this is going to be important now. Because and that what is physically this quantity now, right? Total volume in the case of occupied states divided by volume by one state is the total number, or the particle density, right? Sorry, this is the total number, not even the particle density. It's actually the total number of states in this whole metal. And if I want to find the per unit volume, what is the density, particle density, I must divide by the volume, right? And so that essentially gives you a very nice picture of, if I have a single particle density of n, then I can relate it to the kf. N is typically what, 10 to the power 22 or 23 per centimeter cube, right? In a metal, that many conduction, or that many electrons in the band, and therefore kf from here. You can write down, it goes as the cube root, so the 4, 2, and 8 all cancel, and you get like a 3 pi squared times n 1/3, right? So you can you can calculate what is the Kf right away, and from there you can calculate what is the Fermi energy. So these are relatively easy things, right? Meaning you can put this in here and calculate what is the Fermi energy right away, right? And what is the number roughly in order of magnitude for a typical metal? Anybody? What is the energy in electron volts in a typical metal? Yeah, it's an order of magnitude 5 eV, 10 eV, something like that. Depends upon the electron density. It depends on it as 2/3 k squared, so 2/3 power. So the point here is the Fermi energy will, from here right away you can get its, I'm going to just call it 10 eV. It can be a little less, 4 or 5 eV. You can calculate it. It depends on the carrier density, right? And this is an important energy scale to remember. And what does, why am I kind of discussing this at this point is because of the Pauli exclusion principle, if I were to put some more electrons into this object, this entire space, in K space, in energy space, is forbidden. I cannot put another electron inside this sphere. Right? That's Pauli exclusion. That's excluded by the Pauli principle. So, and so there is no such restriction for bosons. If I have bosons, for example, I have I may have photons, or maybe a very good example is a helium atom itself. The atom, if I have helium-4, helium-4 atom that has 2 protons, 2 neutrons, right? And that's your nucleus, and then it has 2 electrons. So that's your helium-4, and there are 6. So each of these particles is a fermion, but you have 6 of them. It's an even number. So the total spin is now an integer, and so it becomes a boson. Right? So helium atom, I mean, not even single electron. Now we're talking the whole atom. It's a boson. Right? And now if I take helium at, as you know, helium is a gas at room temperature. And then you freeze it, right? And you know that so it will have a certain temperature in which it will become a liquid. Actually, let's start there, and then around 4.2 K or something like that, right? It becomes a superfluid. No, is that correct? No. The temperature is something different here. Liquid helium, and then because these are bosons, as you lower the temperature. So let me just write it this way. I forget the exact temperature. 2.3 K. I think that's the right temperature. So it becomes a liquid at 4.2, around 4 Kelvin. It becomes a sorry, was it right? Gas, and then liquid, and then a superfluid, right? And then around, I forget exactly, it was 2.3 K or something like that, it becomes what you call as a superfluid. And this is very interesting because this is what Kamerlingh Onnes, who really discovered superconductivity, he did it for the first time. He was able to liquefy helium. And in fact, he had also frozen it down even further. And if you, I think people are just discovering his notes, more than 100 years after he did it, and he had also observed superfluid, but he didn't realize what he was seeing. Basically, superfluid is when the whole liquid is going to flow with no viscosity, no resistance. It will be able to climb up the walls and all that. It will flow with no resistance at all. Now, this is a flow of atoms, not even electrons. Superconductivity is electronic transport, but this is flow of the whole object, which is each atom is a boson, and they have condensed into a Bose-Einstein condensate, and that's a superfluid. So superfluid, when the major difference, qualitatively, the difference between a superconductor electric current and a current of matter atoms here is this is not charged. It's not a charged object. Whereas in a superconductor properties are pretty much the same as a charged superfluid. Each particle is carrying charge now. So that's the difference. In fact, And then here the liquid flow or transport of atoms is frictionless. In the superconductor, the transport of current, charge current is dissipationless. In fact, what is very interesting is helium-3, which is an isotope of the helium atom. And the major difference between helium-4 and helium-3 is there is one missing neutron. There's one less neutron in the nucleus. So you have 3, that's why it's called 3, right? 2 protons, 2 electrons for charge neutrality. But now you see you have a half integer number of spins now, 5, right? And so this helium-3 is actually a fermion. And whereas this is a boson. Just from Fermi statistics and or rather the spin statistics theorem, it's just boson, right? Now this is very interesting because you can take also helium-3, right? And I forget exactly at what temperature. Maybe some of you know, or so around 2 Kelvin maybe. I forget exactly what. It becomes a liquid too. Liquid. So for example, if you are doing experiments and you want to go to 300 millikelvin, that's 0.3 K, you would need helium-3. And helium-4, maybe you'll run into some trouble because of superfluidity and other things. You'll run into some trouble. But if you want to really go to below 2 Kelvin or lower, much lower, into hundreds of millikelvin, you need liquid helium-3, and that costs a lot more. It's very rare. In fact, it escapes the Earth's gravity, so Earth is losing helium-3, so its price is also going up. So it's, anyway, but what is really interesting is because it's a fermion, people believed for a very long time that there's no way it can form a superfluid, because it's a fermion. Why would it condense into Pauli exclusion principle will forbid it, right? And so to actually a lot of people, to great surprise almost, but not quite that much of a surprise, people who understood, what superconductivity implies, realized. So around, I forget exactly, early 1970s, here at Cornell, Doug Osheroff was a PhD student, and Bill Richardson and Lee, they froze it down to really low temperatures. I think it's to something like that. I forget exactly. Very, very low temperatures now. And then they observed that also becomes a superfluid. And now that's very weird, right? Because it's actually a fermion, but it still condenses and forms a superfluid. And we're talking about atoms here, right? I mean the whole object, and then they were recognized also with the Nobel Prize, because very interesting that a fermion can form a condensate, and that is related very deeply to the fact that electrons also condense into a superfluid and form form a superconductor, a charged superfluid. And the reason for that is exactly the same as the reason why electrons condense. Because when we take 2 fermions and you turn on some sort of an interaction between them, which is attractive, and this is the main idea. If I take 2 fermions and I turn on any sort of interaction between them that is attractive, no matter how weak, as long as they attract, it is basically it's inevitable that it will condense into a superfluid. It has to happen, and that's what Cooper found. He found a way that electrons could do it, right? And experimentally, obviously, people had already seen that, but theoretically, the reason why it occurs is really shown very clearly by the fact that even helium-3, which is clearly a fermionic atom, also forms a superfluid. It requires a lot lower temperatures and more extreme conditions, but so the idea is if you have 2 fermions, or if you have fermions and you turn on some sort of attractive potential, what does that mean? That the interaction energy between them is negative. So they would rather be closer, to lower. But by forming a pair, they can lower the system energy. That's the meaning of it. If you can create situations where the all other energies of the system are much smaller than this, then it's inevitable. It's its fate that it must condense into a superfluid situation. Right? So this is, and what we want to see is how does this happen for electrons. Now that's really what we want to see, and we know quite a bit about the electronic microscopic properties through electron-phonon interactions, and the fact that the experimental data pointed towards the role of phonons is what led to the BCS theory for superconductivity. Yeah, there was a question? None? Okay. All right. So let's. Right. Yeah. Okay. So let's look at again the microscopic picture of why the electrons may have an attractive interaction, and in spite of all this exclusion principle, they can still form a condensate or form a pair. We'll go step by step. We'll first explain how can electrons attract each other, and then we'll see that here are some of the results that we'll come to. So we'll see that electrons, if I add electrons very close or slightly higher than the Fermi surface, just around this sphere, around an energy, around the Fermi surface, I take a very thin slice, and the energy of that slice is roughly h bar times a phonon energy, maximum energy of the phonons, roughly. Its optical phonon energies are tens of MeVs or something like that, around that energy. In that thin slice, thin shell around this Fermi surface, I'll find that there is a very high chance that an electron, let's call it K1 here, and with a say up spin, it can have either spin, but I'm just choosing that state, K1 and up spin. It will actually form a pair. It will form an attractive pair with a diametrically opposite electron on the other side of the Fermi surface, diametrically opposite, on this side, which has a momentum of minus K1, comma, spin is opposite, down spin. They'll form a pair. We'll see that. There are other possibilities. The other states can also form pairing, but the pairing will be the strongest. The pairing interaction will be the strongest for these diametrically opposite states on the Fermi surface. And so that will form a pair, that will form a pair, and pretty much all of them will form pairs around this. And the condensate will be one state which is, basically all of those pairs together, all the pairs together. So if there are big N electrons forming pairs, then there will be N by 2 pair states, or Cooper pairs, and all N by 2, the wave function for all of them together will be what we have talked about earlier. That's the macroscopic wave function. It's one wave function for all those big N by 2 Cooper pairs together. It's one wave function. Right? So that's what we are going to look at. How does that form and why and so on. Right? And what we will see is this pairing energy. Let me just write those things down because if the discussion leads me to other directions, I sometimes may not finish. But this is typically, let's label it as omega d. It's kind of the maximum phonon energy related to what's called the Debye frequency. Omega d is called the Debye frequency. You can think of it as an optical phonon energy. And what we will see is because of this pairing interaction, we will call that pairing interaction energy for each Cooper pair to be, let's call it like V naught. What does that mean? That if it forms a Cooper pair as opposed to free particles, the system lowers energy by minus V naught. That's the physical meaning, and it will be about it will be very small, milli eV or something like that. This is the lowering of energy because of the pairing, because of forming a bound state. And what we will see is the total energy of the entire Fermi surface, all these electrons together. The total energy of all these electrons together, I think you can calculate very easily if in the single particle picture, right? Each state has h squared k squared by 2m, and you just sum it over entire sphere, you get the total energy, right? Does that make sense? Yeah.
Wait, you're assuming the non-interactive case?
Yeah. For which case? You mean for?
When you can just sum over.
Yeah. For the exactly right. So if I ask you, well, tell me the total non-interacting single particle energy of this entire electron distribution, that's an easy thing to do, right? You can just sum over all h squared k squared by 2m, you get the total energy, right? And that's something I don't want to write right now, but I think it's like 3/5 times, when you sum over all states, you get something like that. So let's call that's the normal metal state total energy. But because of this pairing, what we will discover is that the total energy is going to be lowered by a certain amount, and that's the reason why the system goes into this lowering, from here to there. How much energy can the system lower to form a condensate by pairing? That energy is what we are going to call as the gap of the superconducting gap, and what we will find is this gap is going to be given by. It's going to be related to this shell of energies, which is optical phonon energies. And it's going to be 2 times that times e to the power minus 1 over this interaction, or the attractive potential V naught is going to appear here. And the other term that will appear is the density of states at the Fermi surface. Outside, not inside here, but on the surface, Fermi surface, the density of states, and that's typically written as an n of EF, or sometimes G of EF, depends on which book you read. And in the original BCS paper where they derived it, they actually chose to chose to write it as half, meaning a density of states for each spin, because each state has 2 spins. So they chose to write it as half. Those details are not terribly important, but I posted BCS paper, so this is what you will see. This is the expression for the gap, and this is the reason why the superconductor exists in the first place. Why a metal turns into a superconductor, because the system of electrons can lower its energy compared to its normal metal state. That's the main reason why it actually does it, right? So it's a thermodynamic phase transition into a lower energy state. And that low energy state is what we are trying to understand at this. We looked at its transport in many variants in the last class, but now we are trying to see the reason of its existence. Right? So, okay. So that will be the gap, and physically, what I would like to kind of say then is if I look at the conduction band states and I look at the density of states n of E, so that the density of states for a 3D metal looks like that, right? It goes as square root of energy, right? And it is filled till a certain Fermi level, right? That's the Fermi level. And normal metal at very low temperatures will have these states filled and the states above it empty, right? So that's how the density of states picture will look for a normal metal, and if this same normal metal undergoes the superconducting transition, now what's going to happen is its density of states will look very similar, far from the Fermi energy. Nothing changes really deep inside, and those carriers don't change. But at the Fermi energy, what will happen is it will have a gap, something like that. So, so this is the gap we are talking about, the delta that we wrote here. And this is the gap that in the last class we talked you can measure with tunneling spectro. You have metal insulator superconductor junction, and this was measured right after the prediction by Ivar Giaever and others. This is the gap you can measure from tunneling currents. So one of the interesting things in this picture about this result is the gap depends on the phonon energies. So materials that have large phonon energies will have larger gaps. How do you get large phonon energies? Light atoms, maybe. Lighter atoms will give you larger phonon energies because the phonon frequency goes as 1 over mass, or square root of mass. So lighter is the mass, higher is the phonon energy, right? But I think you can see this is not the most important term here. It is obviously important, but not the most important. The most important term is what's sitting here, right? Because it's an exponential. And the pairing energy is also important, but really what you can change in different materials is the density of states at the Fermi level. That you can change. And so what you'll see is typically metals, or even, by the way, when I say metals, just I can, for example, heavily doped semiconductors can also undergo superconducting transition. Most of silicon, diamond, germanium, all of them have shown superconducting transition if you dope it very heavily. When you dope a metal very heavily, you are effectively degenerately doped, and it looks like a metal again now, right? And it's just that anyway, so that they can also show superconductivity. From this picture, you can see that what you would like to have is this exponential term as small as possible, so that you get a large gap. And the Tc, or the critical temperature, is, there's a certain factor here which I don't want to bother with at this point. It's of the order of delta. The critical temperature is of the order of this gap. Kt is the order of the gap. So if the gap is larger, you will have a higher Tc superconductor, right? So that's the other thing here. And so to increase the gap, you can play these games. And what I was trying to say is one of the most important things you could do is make sure that whatever is sitting here is as small as possible. And how do you make that sure? You want to choose a material that has a very high density of states at the Fermi level. That's your main tool for normal superconductors or BCS superconductors, right? One way to kind of just qualitatively at this point do that is, if you are choosing a material, you have an option to have the energy at the Fermi level, the orbitals that form the energies at the states that form form the eigenstates at the Fermi level. You can have them formed by s orbital overlaps, p orbital overlaps, d orbital overlaps. So you have different choices, right, as you go through the periodic table. And typically, if you have s orbital overlaps, I think that the density of states due to s orbitals or p orbitals, they look something like that, right? From your E of k is the band structure, the hopping terms times cosine of Ka. We have talked about this from a simple tight banding picture. And the bandwidth of any band is 4 times the hopping integral, the width of a band, right? And if you have s orbital overlaps, it's actually can hop very easily, right? So the T is large, it can lower its energy, by hopping easily. And so as this is large, so the maximum density of states you have is not very large, because the total number of states is the same, right? Does that make sense? So an s orbital band, for example, may look something like that. And let's say I want to form, I'm trying to design a superconductor, and I want to see how much n of E, and I place my Fermi level here because that's the maximum value anyway, right? This is the density of states we're talking about here. So I'm saying a S band will not give you as much density of states at the Fermi level as the other orbitals like a p or a d orbital can, because d orbitals really don't want to hop. d orbital states, I just sketch one of them, and these are much more localized, or d orbitals are much more localized. They're not as easy, they don't want to share electrons easily. So the hopping term becomes very small for d orbitals, and as a result, the band becomes very narrow. Bands are narrow, effective mass is very large, sluggish in terms of its movement. So what I'm trying to say is what you will see in periodic table, also in the metals that actually show good superconductivity, the Fermi level states are formed of d orbitals typically, and this is kind of also the reason why it actually helps with this picture. So niobium, lead, all these things, they're d orbital transition metals. That's what they lead to. Again, whatever I'm saying is sort of, you have to understand that we know that diamond also forms a superconductor. So clearly, there is a possibility of doing that even without maximizing the N of E. But yeah.
So greater effective mass gives rise to better superconductivity in accordance to the
yeah. Yeah, so mass, yeah, that's right. If the band is narrow, then the mass is larger. Yeah, that's correct. And which is very strange, because you would think that it will lead to a lower conductivity, the standard conductivity, and that's true. The materials that show high, good superconductivity are actually not very good metals. And on the other hand, they form, so and the best metals, the best highly conductive metals like copper, and silver and gold, people haven't been able to make them have not observed superconductivity yet. And they're very good conductors at low temperatures, but they're not superconductors, meaning I said earlier that it is inevitable it's going to form superconductivity. Its TC is extremely low. That's what we mean to say. We have really not been able to. Yeah.
That's a plot of energy versus density of states, not E versus K, right?
This is exactly right. This is density of states versus energy. And your EK diagram, for example, for the s orbital will look, whichever way, it has the bands and all that. And this is the density of states we're plotting here. So what I was trying to say is, if you want to really get a very high value of density of states at the Fermi energy, you're better off choosing orbitals that don't, electrons, the hopping terms are small, rather than large. So yeah.
Or would you use F orbitals too?
If you can, this is kind of a general trend, and you can take it for, which is correct. Nowadays, if you're looking at some people who are looking into DFT design of high temperature, or increasing the TC, that's what they're looking into, which orbital, what do I couple, how do I maximize these things, and that sort of thing. So yeah. Okay. Good. So let's now look at, by the way, the BCS theory also gave you, that the superconductivity changes, at the critical temperature, the material becomes superconducting, but then as you go to lower temperatures, so essentially this is a very different kind of gap than a semiconductor. In some senses it's similar, but in some other senses different, in the sense that that the gap will go way above TC, it becomes a normal metal. So the gap depends on temperature. How does it depend on temperature? It's plotted there. So the at 0 K, the gap is what we have calculated here. There's no temperature dependence, right? But it will decrease with temperature, and at TC it will go to 0. So and becomes a normal metal, right? So that's the idea, and this is what the BCS theory predicts, and you can see some of the examples of experimental data on it, and it's kind of nice. It fits, and this is. Okay, so let's now discuss the microscopic picture of what is the reason for pairing. Okay. So the reason for the pairing of these electrons on the Fermi surface can be looked at it this way: that if I have the electron going through a lattice or a crystalline lattice, right? Okay, so maybe I'll give one more. Yeah. And the electron is moving through here, and here are basically the atoms sitting on the lattice sites, and it's a, we can think of it, it's a metal, so it's the core, the nucleus is positively charged, right? It's all protons. And some electrons are shared, some are not, and all that. But if the electron is here, we know that this is a positive charged core, so it will get attracted towards the electron. It's like, right? It'll pull so instead of being right here, this atom maybe it's highly exaggerated. Maybe it has moved a little bit closer. Similarly, this one has moved a little bit closer, and it has formed around it a cloud of distortion of the atoms. So it has distorted the lattice, and maybe far out here the change is not that much. It's still around here, but very close to it, it has formed a little distortion. There can be nearest. There'll be a little bit more less in the next atom and so on. But essentially they have all been pulled a little bit towards it. So now if I forget that the electron is there for a second and look at this whole charge neutrality picture, originally if there was no electron going through here, this was positive charges on a lattice, and now I can see that this region has a slightly more positive charge right here, around here, right? So the electron is around it, dragging around it a cloud of slight positive charge, right? And if there is another electron somewhere around here, it says, oh, there's a positive charge there, it would try to get attracted to that point. But then these two electrons will repel, right? Coulomb repel, and this positive cloud will attract that other electron. Right? So that much is clear, right? If I have a slight positive cloud, it should attract an electron, but then if there's an electron sitting there, it's going to repel. Right? Is that clear? I mean, and that argument should be hopefully easy to understand. But how is it then that the electron is able to overcome the repulsion? That's really the key. And let's look at it this way. This electron, what is the speed at which this electron is moving, right? That's what you call as the Fermi velocity. Remember, these electrons we are talking about are on the surface, the Fermi surface here. So it's moving with Fermi velocity. And if your Fermi energy is 10 eV, right, you can write, half mv square is Fermi energy. That's 10 eV. So Fermi velocity, what will be the order of magnitude? You can help me here. Yeah.
10 to the 6 meters per second.
Yeah, that's about right. So 1/300 is the speed of light, 1/300. So roughly 10 to the power 8 centimeters per second, or 10 to the power 6 meters per second. That's correct. So if so that's the speed with which the electron zips through here. It's moving fast. And what do I mean by fast compared to what? It's very fast compared to the movement of the ion itself. The ion is very heavy. It has protons and neutrons, which are much heavier than the electron. And for example, if I were to look at a plot here of the distance from the electron to basically this distance, let's call from one lattice side, from here to there, this distance, okay? And I plot how much has the lattice distorted, the delta U, let's say, the distance over which this del U, how much has it distorted, how much has it moved, how will it look? This is an interesting point, because you see this electron is moving with this speed, but the atoms themselves can vibrate at their phonon frequency. That's the frequency at which they can move, right? And what is a phonon frequency on the other hand? So a phonon frequency is of the order of 10 to the power 12, or about the order of magnitude a terahertz. That's the speed at which the atoms vibrate. Roughly order of magnitude. Yeah, there's a question.
Is this related to the bifrequency?
Yeah, you can call it the bifrequency. So, I mean, it's basically the maximum frequency of phonons, or maximum energy of phonons. H bar omega is it's the Debye frequency. You can be more precise if you want. Is it optical phonon? Is it acoustic phonon? Whichever. But this is the order of magnitude. It can be 10. It can be, so it's a terahertz. It can be 10 terahertz or 5 terahertz. But this is the order of magnitude. So, as a result, you can actually see that. And it's very similar to a light mass and a heavy mass, interacting. You know that the light mass is much more agile; it moves through, and the heavy mass is much more sluggish. So here the electron actually moves very fast, and when it's physically here, these atoms have felt the force, but their inertia is holding them back. They are not yet distorted, and the electron goes away. But they have felt the force. That means they have started moving in now, right? But then by the time they reach somewhere, they get distorted. They reach their maximum distortion. This electron is far away. It's gone. Right? Does that make sense? It's gone. So this response is retarded. It's not an instantaneous response. It's a retarded response. So this is the distance of the electron from this region. So I'm plotting x here. So when x is 0, the displacement is none. It has not been displaced at all. Even though it has felt the full force of the electron, it has not yet displaced. And when x is really, really far away, then there's not much force either, right? But essentially, you can see it will look something like this. It will take some time or only when the electron is some distance away, it's going to reach its maximum distortion. Right? And this is what's called the Cooper pair length for a reason, for a good reason. That so this distortion stays here for long after the electron is gone, and now there is enough time for another electron to come in, and there is no electron here to repel anymore. Right? You see that, right? So this is this electron is far out here, and now another electron comes in here, and this thing essentially starts. You can see that this is really the reason for the pairing, that the electron can now remotely attract another electron, and the Coulomb repulsion is much lowered because it goes down as the distance, but then it's also screened out and all that. But the attractive repulsion is retarded, so it is able to take advantage of attracting another electron, and this is how they form the pair. So if electron is very far out here, they'll form a pair now, and then they'll move in unison. Yeah. Right.
How is this different from a polaron?
It's a good. So a polaron, this idea of pairing came from the polaron theory too. I mean, so a polaron is where the electron is formed a composite object with this lattice. So essentially, you can consider this lattice distortion and the electron together as a polaron. It's one object. Polaron doesn't have the other electron in it. So another way to look at it is the lattice is distorted enough that the electron it's like a soft mattress, if you might, right? And the electron has formed this. This is a polaron. What is a Cooper pair? A Cooper pair is when an electron is here and the other electron is here. They will actually attract now. So that's the difference between the two. And what is this? This is really the energy landscape that the electrons are seeing as they're moving. And then there's a little distortion left, and the length of this is the Cooper pair size. And what I was trying to say is this is what's called the coherence length or the Cooper pair size or all these things. And we can estimate it in a couple of steps. What should the length be? Yeah.
So is this effectively like the strain?
Yeah.
The delta U, and when it reaches
Absolutely.
the maximum strain,
That's right.
they form.
So it doesn't have to reach its the when is a time dependent phenomenon. Yeah. So when the electron goes through, it is going to distort it, right? And that distortion stays for a little time. The atoms move in and move out and all that, and then it maybe rings a little bit and then goes away. So but then that is enough for it to capture another electron, and that electron will, as a result, get tied to this, and as it's moving through, it will move in unison with it. So that's the idea. Yeah, right. Yeah.
So from this picture, if you have, let's say, material with a low triple R value, and you have a lot of defects, is there a relation, meaning are those defects causing sort of scattering of that electron, and then the repair coherence length to be shorter in this case? So do you know if there's a relation between the coherence length and triple R?
Right. So it's actually a good question. I'll kind of step back a little bit. Once you form this condensate, it is completely, agnostic. It doesn't care about what defects you have anymore. It forms all these things form a correlated state, and you cannot scatter one electron anymore. I mean, you have to scatter all of it together because it's one object now. Right? Do you know what I mean? Because it has gained strength in numbers now. It's a cooperative phenomena. Meaning, instead of thinking of it as individual electrons, going through the lattice, you must think it as one big object going through, and one defect cannot scatter it anymore. Meaning, right, it cannot dephase the whole object anymore. But defects do play a role in determining, coherence length and things like that. Definitely, they do, right? But once you're superconducting, it is going to be independent of defects. The coherence length may depend on the defects, but it will give you zero resistance still. That's the point. Yeah. There's one more question.
I'm just having trouble rectifying this.
Yeah.
This microscopic picture with the fact that electrons with opposite Ks are pairing.
Yeah. Yeah.
It seems like they would have to be moving kind of the same direction.
Oh, yeah. Good. Very good point. So this is so. We'll look at the reason why. By the way, this is, again, think of this as a qualitative picture, and there's no problem with another electron moving in another direction, pairing with this electron, meaning that electron may be was coming this way and that this electron is going that way, no problem. It will still couple, So that's the idea. And it's a little difficult to kind of relate it in real space, but this is really true, that this is the nature of coupling. And it could, in principle, couple to any other state here, but we'll see that to form the gap, to minimize the biggest lowering of energy you get is when they are diametrically opposite. And they must also have opposite spins for what we call as spin singlet or S-wave superconductor. And that is very important. In fact, exactly how this microscopic picture is one possibility, and most people believe this is the main reason. But it need not be. There are other ways of pairing. You can have on-site spin-spin interaction or antiferromagnetic order related pairing that does not even invoke lattice distortions at all. There are other ways to pair as well. But the spins must be, and this is a very important concept, meaning an electron going this way must have upspin, but if it's going that way, it must have downspin. And this is starting to look like what we will do later, which is the topological insulator, where you actually have this situation. Spin and momentum are locked. And if it's going to the right, it is upspin, and going to the left is downspin. And what you really need for superconductivity to occur is what is called a time reversal path. If an electron is able to go in one direction with upspin, it should be able to traverse the same direction, same path in real space. But if it traverses this way, the upspin is not allowed. It's only the downspin that's allowed to traverse it. So that's the thing that actually is needed to get pairing. Okay, so this length is relatively easy to calculate now, because we know that you have two parameters here, and I think you can probably see that the coherence length should be of the order of the Fermi velocity times the by of the order of that, because that's the time, tau, which is the time it takes for this to respond, is 1 over that, right? So that's the length, and from here you right away get it's 10 to the power 8 centimeters per second divided by 10 to the power 12 per second. So you get about 100 nanometer or something like that. This is the length, the distance over which they're interacting. 100 nanometers. It's actually a pretty large distance. And, it could be 50, depends on some other details, but this is the order of magnitude, the size of a Cooper pair, and it's also called the coherence length for many reasons. And it's not a few angstroms. That's important here. It's not a few angstroms. And by the time two electrons in a metal are 100 nanometer apart, there is basically no Coulomb repulsion. It's done. It's all screened completely, right? So as a result, here's how Froelich was trying to explain why they can pair, but it didn't quite finish the story. So here's a picture to look at. So I have an electron go in. I'll try to draw this space-time diagram. Electron coming in with a certain momentum, say k1. Okay, this comes in, and this time I'm going to draw time this way. I think this is probably the standard way of drawing. So electron comes in with a certain momentum k1, and then it emits a phonon. You can think of this distortion as a phonon wave, right? And it emits a phonon, and then changes its momentum into k1 prime. It changes its momentum to k1 prime, and this phonon carries a momentum q, or h bar times q, and there's another electron coming in with k2, and that absorbs that phonon and goes out as k2 prime. So this is a scattering event between, it's an electron-electron scattering by the exchange of phonons. But that phonon is not visible to the outside world. All the interaction happened between these two electrons. You can't observe it from outside. So that would be called a virtual interaction. In fact, all forces we know, even the Coulomb interaction, why do two electrons repel, is also understood in this way. Why do like charges repel and all that? So electron will come along and it will emit some photons, and then that's how they interact, and that's why we get repulsion between like charges and attraction and all that sort of between unlike and so on. So here's the picture that you have phonon emission and phonon absorption, and in time, it's the time sequence is this electron first emits and this electron absorbs later. And so we can calculate what is the energy associated with this diagram here. We can calculate how much energy, and that's what's going to lead us towards this delta picture here. How much energy lowering can this process give you? How much energy lowering? And I'll just kind of write this out. It's explained a little more detail in the notes, but that are posted. So this electron, at this point of time, you can find out the total energy. Let me first point out that you know how to find the amplitude of this process. That's a matrix element of phonon emission. We have actually calculated it in a phonon emission matrix element where you go from k state to k prime state with a certain phonon matrix element here. Right? We have calculated that. That's amplitude of that process. Right? And here you have multiple things happening. So you have let's consider what happens at this time instant as our initial state and what happens at this time instant as our final state. Okay? And the initial, so my total energy, I'm going to be, so I'll write it this way. The change in energy that this process may give you is given by the following. So you start out with the initial state, and whatever happens in this process here, then you end up with the final state, and this quantity must have some nature like this, right? This has units of energy, as you can see. Right? But this particular process is two scattering events, right? One here, the other there, and it's two particles too. It's two particles. So the way I would write it is you start out with the initial state here. I'm not going to bother too much about the matrix element exactly what it looks like, because it's basically, you can write it as deformation potential matrix element that we have done for phonon scattering. I'll just write it as M, as my matrix element, and that's not exactly important what nature it takes. It is related to h bar and omegas and all that sort of thing of the phonon. We have calculated that, but what I'm really interested in here is M from K1 to K1 prime. Is what are the changes in energy? And if you remember, you solved an assignment problem now where you have something that looks like this, initial minus 1 over the difference in energies. And then there will be another term here which will be essentially the complex conjugate of that, K1 prime, K1, is complex conjugate terms. So this is the processes that are occurring here. And at the initial state, my energy is the energy of this electron plus the energy of that electron, and there's nothing else. There's no phonon yet. So that's my initial state, E of K1 plus E of K2. And the final state here has this state. There is a phonon still, and there is a final state here. We're choosing that instant at which that absorption process occurs. And it's going to be K1 prime plus E of K2 prime plus h bar omega of the phonon. So this is how it's going to look as the total matrix element, or the change in energy. The lowering of the energy of this whole system because of this particular process occurring. If this process doesn't occur, then the energy is just ek1 plus ek2. There's no change at all, right? But if this process occurs, this is how much change it can do. Yeah.
Isn't the phonon gone now, though?
Say that again?
Isn't the phonon gone in the final state? Hasn't it been absorbed?
So it's a virtual process. So physically, it takes some time, 1 over tau sort of thing to occur, right? That scattering rate or absorption rate. So by this time, I can say that. You're saying that I should not include, so okay, maybe the initial time I should put it here, and that's clear, right? But if I put it here, then everything that crosses this point I must include its energies. This is virtual energy, right? Again, I mean, this is I'm trying to motivate exactly why there will be a lowering of energies, but this is a Feynman diagram, and Feynman's approach is, you must sum all processes, not just this per process, all processes like this. So there's another possibility here, for example, that instead of this one emitting and that one absorbing, this one can emit and this can absorb, and that will kind of do it will look a little different. That this will emit and this will absorb, and the initial states and the final states may look exactly the same, but the process is now reversed. The time ordering is reversed, and in that case, what you will get is, in fact, you will get a minus sign here instead of a plus sign. And you sum these two things. Let me write down the final result. In fact, it's not terribly important to see exact details because this doesn't give you the exact numbers, correctly, but it gives you the reason why it should pair. So when you sum these two, what you are going to get is a very interesting. So there'll be a plus h bar omega here, and the other one will have a minus h bar omega, and this whole energy difference or lowering of the energy will look like this: E of k1 prime and minus h bar omega q whole squared. This is how it's going to look, the difference of the two. Sorry, the sum, not the difference. So this plus numerator terms, and then this will become minus h bar omega q. Right. And all these energies are really close to the Fermi surface, so EK1 and EK2 are very similar. I mean, they're pretty much very similar. They're just maybe a little off by h bar omegas, which is the diphonon. But this is how it's going to look. And if you make a plot of this, it will give you. Remember, what we are doing here is the change over the normal metal situation. Normal metal, will have an energy that is very well defined. This is the energy lowering compared to the, if you didn't have this process. If you have this process, this is how much the energy can lower, or the change in energy. It doesn't have to lower, right? This is the change in energy. And if I make a plot of this now as a function of the difference of EK1 minus EK2, this is the K1 and K2. What you see is it blows up at one point, which is at the phonon energy h bar omega. And if this term is small compared to h bar omega, this whole thing is negative. Right? It's negative. So this interaction energy, I shouldn't call it just delta. It's not the gap yet. But so essentially, it looks. It has a finite value, and then it blows up. Right? And then this is h bar omega q, and then above it, so it's positive, and this is negative. Right? So what it's saying is there is a chance for you to lower the energy. This is lowering of energy means it's attractive. The interaction is attractive now, right? And the more you can lower, the better it would be, right? So as a result, if this is as close to this, if it's very close, then you can lower your energy even more, right? And so, meaning the lowering of energy is larger if you're close to this, which is why we have this reason that all the interactions occur within a very thin shell, which is the phonon energy shell around the surface, Fermi surface. So, this is, right? So it can lower its energy a lot. In BCS theory, what they assume is they kind of, because qualitatively, once you understand this, quantitatively, you can make some approximations, and the approximation they make is this lowering of energy is just minus V naught. Constant. I don't want to bother about exact details, and that's the minus V naught that appears here. That's the lowering or pairing energy that appears there now. Right? So is that clear? I mean, this is just a way to explain. You may also ask, hey, what about the Coulomb repulsion? The Coulomb repulsion, you have also calculated that. In your current assignment, you are looking at a Coulomb potential V of R is e to the, basically it's charge squared by 4 pi epsilon times 1 over R if it's unscreened. And if it's screened, it's e to the power minus R over some Debye length, right? So you have done that. And if you look in the K space, you will see that the Coulomb potential will also lead to a change in energy, just like this, except that Coulomb potential will be, the change in energy would be the Fourier transform of this. This is directly, that is the Coulomb potential, and that happens to be E squared by dielectric constant, and you get Q squared plus 1 over Debye length squared, something like that. You'll get that from Coulomb potential, and this is always positive. Right? So it's a competition between this term and that term. This is what's attracting the electrons. This is what's repelling the electrons. Right? And what I was trying to say is, if the electrons are really far apart, Q is 2 pi by the distance, if you might. It's very small. And no. I mean, okay. So I didn't mean to say. It's essentially this term and this term. When this energy gets smaller, for far enough electrons, the screening is enough that this can be completely neglected, or you can include it and find out what's the this will just shift a little bit here. But you will always get a negative part. And then that's the key behind condensation, or rather pairing. This is the idea behind pairing. Right? Okay, so I didn't say much about what, so all I have said is the pairing, you can get the biggest bang for your buck in pairing if you choose states that are right on the surface, within a phonon energy array. I haven't said why should it be diametrically opposite yet. Right? And that you can understand by looking at the following argument, that if I have the electrons, say K1, so K1 is, remember, the initial here, and I want to show why K2 with which it will interact or pair should be minus K1. That's what I want to show now. Right? Why should it be diametrically opposite? So right now we have only talked about any two, K1 and K2, as long as they are separated by just the phonon energies. Right? So if this is K1, I can draw like a Fermi sphere around it, saying that, well, these are all the energies, which is the Fermi energy. Right? And I also know that there's a little shell around it. Those are the states it can scatter into. K2 should be around in there. Right? But if K1 and K2, let's say K1 plus K2 is equal to some wave vector, big K, right? And I can plot this as well. Instead of plotting it this way, I can plot it as K1. Okay, no, that's fine. I can plot it K2, the same thing. So I can sketch K2. Let's K2 call K2 to be something like this. I want to show why it should be this way, not this way. If K2 is like that, I can, or let's call K2 is like that, right? So you can see then big K, which is the sum of the two wave vectors, would be something like this, right? Right. So if this is K2, and I want to actually just translate it here rather than there, I just want to show K1 and K2 this way. That's right. And the thing is, the K2 will also scatter into, or once you the K2 prime that we looked at here, K2 prime will also be within a thin shell around its radius, right? So the K2 prime, the final state it scatters into, will also have a shell like this. I hope it makes sense what I'm talking about here. So K1 and K2, this is the big K, which is the total sum of the two momenta. And what we are saying is, because of this interaction we talked about, this can only go into states that are little ring here, and this can only go in. Does that make sense? The two rings, or the two shells, must overlap in the region where it's favorable for both of them to scatter, right? And this energy here, or this spread here, is of the order of h bar omega Debye. So you see, and this is K vector, and this is basically a circularly symmetric around, right? And this area is telling you what is the final density of states for scattering, or getting into. Does that make sense? I mean, this is the only possible thing if your big K is like this, right? And let's make the big K a little smaller, in which case you see that these things will, and the overlap area will actually increase. You get big K even smaller, and finally it goes to 0. You see that the two shells fall on top of each other now, right? And your total scattering area is the entire shell here. Does that make sense now? Or is it contorted? So this is the big K, which is sum of the two. And from the argument that the electron can maximize its lowering of pairing energy by if the energies are very close and they're just of the order of h bar omega, around. This is h bar omega, so the difference should be around h bar omega, which is the phonon energy. And so that gives you a little window and a little window for this, and this is the overlap region, and this is the final density of states to scatter into, and that is maximized if the big K goes to 0 and the two. And then when that happens, I think you can see that this K goes this way and you are diametrically opposite now. So that gives you the biggest lowering of energy, and that's why the pairing is pairing will occur such that K1 is equal to K2 is equal to minus K1 or something like that. So that gives the maximum change. Okay, so I still didn't manage to get to this point today, but so that these are all qualitative arguments, and to actually calculate this needs a little more, couple of steps, and you can get it. But once we have understood that the reason for pairing, the microscopic reason for pairing, and also identified which K states will pair. From here to get to the final answer, it's now the path is clear, and this is what Cooper did initially. He's able to show that physically it's inevitable that particles on a Fermi surface, electrons on a Fermi surface, will pair and at certain temperatures, and you can see probably why, if I apply a magnetic field, there's a problem. It will flip one of the spins here, and it will cause issues with it will that's maybe a microscopic way of looking at why you can. There's a Zeeman sort of term and all that sort of. But anyway, so this is the pairing reason, and I might need a little more time to get to this idea, and we will maybe do that in the class on Tuesday and finish this topic before we go in the integer quantum Hall effect picture. So please read this posted notes, which are papers from BCS where he explains why the coupling is this way. Okay. And he also explains a matrix picture of it, which is related to perturbation theory, and the fact that you have this lowering or the gap that's formed. But if these things are clear, calculating the final thing is not very difficult after this. Okay, so tomorrow we are doing your first short presentations, and instead of 5, let's meet at 5:30, and we'll do the same thing, meaning some food and all that. We'll get the food a little earlier tomorrow, and just remember it's a very short presentation. I want to see what your topic is. Everybody wants to see that, and just introduce the topic and tell us what is it that you're going to do for the last month and a half left in this semester, okay, for the projects. Okay, good.